11.3. So we're here. So we're done with 11.1. We're done with 11.2, and now I'm going to do 11.3. So this is statistical description of physical systems. Physical systems. And I'm going to get a picture from here. I'm going to paste it here. So the picture on the right represents a box sitting on a ramp. This is the classical mechanics picture of stuff. The box on the left is the quantum mechanical interpretation. So in classical mechanics, things are continuous. So according to classical mechanics, all values from the top of the ramp and the bottom of the ramp are possible. You can have any value in between them. In quantum mechanics, it's equivalent to having your box on a stairwell. So in this case, the quantities are quantized. And what that means is not all values are allowed. So in this case, in classical mechanics, we have continuous range. Whereas in quantum mechanics, quantities are only allowed discrete set of values. So they are quantized, which means rules of classical mechanics do not translate well in quantum mechanics. So classical rules must be replaced when talking about microscopic scale with quantum rules. So there are a lot of rules in quantum mechanics, and I'm not going to discuss all of them. All we need to know is that quantum mechanics makes sure that all the values that we have are quantized. They can only take on certain particular values. So I am going to reduce the discussion of quantum mechanics to one very specific case. So if I take this picture from the book, copy, and I paste it here. What is this a picture of? This is a picture of a string, and in that string, it is clamped on both sides. Can the string take on any value? And the answer is no. It can only take on some specific values corresponding to some specific n, and those are called standing waves. This is a classical mechanics problem. And for people who have already taken Newtonian, you guys are very familiar with these kinds of waves. Standing waves are waves in which amplitudes, in which the wave have to be confined between the two boxes. And so for quantum mechanics, you guys remember doing the particle in a box problem? That's like the most fundamental problem. That's where this comes from. So in this case, for a standing wave, if the length is L, lambda is the wavelength, nodes are points 0 amplitude, and antinodes are points of maximum amplitude. So as you can see, that each of these is a discrete value corresponding to each of these n values. Agreed? So classical mechanics says that these standing waves can only occur at these particular values with these particular wavelengths and these particular frequencies. So the fundamental frequency, if the fundamental frequency, I take it as 0, fundamental frequency, all frequencies that are allowed are integral multiple of this fundamental frequency, where n is an integer 1, 2, 3, 4, 5. If it does not form this particular, if the wavelength does not correspond to this n, what will happen to the wave? It will disappear. It won't exist. So the steady state condition for classical mechanics can be written as lambda j equals 2 over njl. Okay. Also, quantum mechanics says P lambda equals h bar, where h is just the Planck's constant, which in fact I can plug this value in here. So the momentum of any particle P in quantum mechanics can be given by Pj equals Nj h over 2L. I just plugged in these values and moved things around. You guys saw how I did that? So I just moved things around. These n's, in fact, are called our handy dandy quantum numbers. And in our 3D system, the one we live in, X, Y, and Z coordinates, that PJ could be written as PX, PY, and PZ. This is just NXJH over 2L. This is NYJH over 2L. And this is NZJH over 2L. That's just what it is. Which leads me to say that if I was looking for P total, P total squared, can I write this as P squared? Squared. Can I do that? Or can I write this as NJ squared, H squared over 4L? I can rewrite the kinetic energy of a particle with mass m. Kinetic energy is 1/2 mv squared. I can rewrite this as 1/2 m squared v squared divided by m, or as 1 over 2m p squared, or 1 over 2m nj squared h squared over 4l, or n squared j h squared divided by m l squared. Oops, there should be a square here. I'm missing a square. And I should probably also add sum over j, because j could take on any value. Okay, now this equation is important. Why is this equation important? What does that tell me? H is a constant, M is a constant, L is a constant. So that means the kinetic energy that I have only is a function of Nj. From this equation up here, what can I also say? That the kinetic energy, the quantum mechanical energy depends on p squared, which means it depends on the magnitude of momentum, but not on the direction of momentum. That's important. So these are the two things we now know. This leads me to a very important thing. I want you to write this in red. A number of different states that correspond to different directions of momentum may have the same energy. Then all of those energy levels will be called degenerate. And the symbol for degeneracy is GI. And it is used to define degeneracy of level I with energy, which is the number of states having energy EI.